Anybody who will speak something very interesting about the famous monomer-dimer model. Everybody here is welcome to join us for dinner at the usual place at 6:45. But if you like to join us, please let me know immediately after the talk. I'll be standing here and writing names.
Okay, thank you very much for the invitation and for coming here. So I will talk about some combinatorial problem which has certain physical meaning. So I have to confess I'm not an expert in physics at all, so when I will talk about physics, my statements will be probably wrong. But I hope that they will give some idea of what's true. So first part is the story. Assume we have a rectangle, n times n, and assume that at least
here's the physicist, mathematical physicist. He can correct you.
Oh, I'm sorry. I will tell
He has said
a lot of wrong things.
He got talk about physics, but he's not a physicist, so he probably makes some mistakes. So you can correct him.
But probably I'm almost sure he'll make.
I will be very.
Okay, good. Thank you very much. So this is the rectangle, and let's think at least one of these numbers is even. At least one, or maybe both. It's not that much important. So why do I want that? Because I want to consider a number, let's say t of mn. This is a number of tilings of this rectangle by dimers or dominoes. I will call them dimers. So, and this is it's a classical question: how many there are of them? So, and this is a classical result by. I always forget how it's written. Castellan. It's. Is it? Yeah.
There's an arm missing.
Arm missing.
It's being useful. Maybe not.
So, maybe I wrote wrong on the paper. You see, I start mistakes as I promised. Feature and together temporary. Gleb, all this happens in 1961. So it turns out that you can write a nice formula for TMN as certain product. I will not write that formula, but at least you from this formula you can easily get an idea of how fast does it grow with m and n, and the answer is that it grows exponentially in area, g over p times mn, where g is certain constant. G is constant, Catalan constant, and it has a nice formula also. It just doesn't fit into the board. So that's a celebrated result. And of course, after you have such a result, you would like to generalize it somehow. So one option is to put. Okay, so what I will do, generalization, add monomers. So just and there are like two options to do that. One option is to add some constant number of monomers. Let's say I have only 3 monomers or only 5 monomers. Or, which from purely combinatorial point of view seems to be harder, is to put certain ratio of monomers. But this is what I will be talking about, and this is really hard from combinatorial point of view, but not for physicists. So my main quantity for today is what I'll call A, P, and N. This is number of tilings of n times n rectangle with exactly P times mn over 2 dimers. So this PMN over 2 just means that dimers occupy like ratio P of the area. So, and again, what I'm interested in how fast does it grow. So, this is one important thing, and then another important thing is that QP is limit of, let's go into infinity, log mn. So, and then this nice result implies, for example, that if density is 1, so we have only dimers, then the result should be GOD. And another thing we can do is find this one, and this is 0. And this is all what we can do easily, fortunately. So, and then, so interesting thing is that this problem is not that much developed in mathematical literature. So you can find some bounds, but they are not tight. And maybe because this is really hard. I mean, when I try to think about this problem as combinatorialist, I have no idea what to do, because this is ratio P is very hard to control. It's like non-local property and what to do. And what do physicists do about that? So what, first of all, just a couple of words, why are they interested in that? So I will tell the wrong things. So the idea is the following. So you can imagine that as like this grid is a crystal lattice, and dimers are molecules, and then you count number of ways to put these molecules on this lattice, and the point of counting the number is that energy of each configuration is, so its probability of being in each configuration is 1 over the number, and energy depends on probability. So, is it awfully incorrect?
It's okay.
It's okay. so yeah. So this and after all, this F actually stands for free, and this is what they call free energy, or as far as I understood, minus this is free energy. But that's.
The point is, it's a difference between the usual energy and the temperature times entropy, and that object is called free energy. You know, so that's the available energy in a chemical reaction. You know? So that's where the terminology comes from.
Okay. Yes. So thank you. And this actually doesn't involve free energy per lattice, because they divide by like the number of points. So this is like how much entropy each new point brings, like that. Yeah, that's fine. So what they do now, they can reformulate the problem of finding f of p in terms of finding another thing. I will show what the thing is and argue why it simplifies our life. Okay, so let's see. 2 and what? They come and they say that we can just consider the following, generating function. This is purely combinatorial. So this is generating function. Variable z, and coefficient of z to the s is number of tilings with s dimers. Okay, so but it's generating function for mathematician. For physicists, it's canonical and sample. So and then you want again to compute some limit, and now the limit you compute is so to speak multiplicative limit. So we compute. Again, limit n go into infinity, and you take these generating functions and take root of degree mn from them. And interestingly, this will be actually well-defined limit even in topology of in the addict topology. Yeah.
So it looks like when S is Mn, it's A sub 2 something. With like I thought P was between 0 and 1. Or am I not understanding correctly?
He's worried about the P being greater than 1.
Yeah.
Oh, yeah. So, yeah, sure. I had to write Mn over 2 integer part. Here, I just consider all others be zeros.
Okay.
Yeah. Thank you. It's for simplicity. So actually, I would like to write infinity here, just as simple as possible.
But also your notation changed. So upstairs you have A sub P, right? And P was between 0 and 1. And now you have A sub 2S, and S is...
But 2S over Mn. 2S over Mn.
Oh, that only divides the 2S. Okay, from here it looked like you are dividing A...
Sorry. No. It's like one...
Just optically it's...
One entity, yeah.
Got it.
Yeah, I hope I didn't change notation. So, yes, and now, what turns out is that this quantity and this quantity are connected by Legendre transform. So, fact is that they are connected by Legendre transform, and so just mathematically it can be written as f of p is plus okay, so technically speaking, f of p and log of theta are connected by the Legendre transform in p and log z. Okay, so however, these things happen, and actually this is proven mathematically, quite rigorously, but just it's unclear for me how to count this statement. But again, our colleagues know. And what you can get from that is the following equality for f of p in terms of more like power series. It's integral from 0 to p of p to p, where like that. So this is like a large formula. Let me just explain what does mean for us. Okay? For us it means the following. Assume that we somehow manage to compute theta, or at least some part of its power series expansion. Then we can compute some part of power series p of z. We can invert it as power series and plug in this integral, and thus get some part of power series of f2. Okay, so all these formulas, I just don't want to discuss them in detail because I'm not an expert. But the result for us, as for people who want to compute that quantity, is that power series, or actually any other information about theta, imply power series of f of p. So, and this is kind of a clue. Now I would like to show you two different approaches for computing f of p, starting from these grounds. One will be not mine, but very nice. Mine and also reasonably good. So, and the point I would like to make is that both of them are based on very nice mathematically observed facts, conjectures, which I can prove, and I really would like to know how to prove them or how to explain them. If you have ideas, I would like to discuss. So, the first approach is approach by Kong. So, what he says the following. Let's first think not about limit in m and n, But let's fix m and consider limit in m. Okay, so then we can introduce, let's call gm of p, which is the same limit. But not for the whole plane, but for the infinite stripe. Then all these things work out in this stride context also, in the sense that you can consider theta m z limit and then again they will be connected by the Legendre transform, and if you have theta m, pardon?
Has that been shown that again you have an analog of the last formula? Because normally this is tricky, you know. So one has to take usually m and n simultaneously to grow to infinity, right? To get such an inverse Legendre transform.
Mm-hmm.
And the reason is that if you only move one and make a needle-like domain, so it's now a very long stretch, then you get this influence from the boundaries, and so the original f may not be convex. While doing the Legendre transform, you get only the convex hull.
So that's a good question. But I think what is shown is that this G is convex.
Yeah, this is okay. No, but you said you were saying that, and then you get also, and that's when I jumped in.
Okay, yes.
The also is the inverse formula. That works only if if you already started from a convex function to get your theta. No? So then you can also get the convex function back by an inverse Legendre transform. No? But if you didn't start from a convex function, something that has two bumps, right, and do your theta definition formula, you get something that's convex, and therefore you can take a Legendre transform, but that one will only give the convex hull of the original object. See?
Yeah, but so which of these two functions you suspect to be non-convex? And just so. Okay, let me put it this way. I'm sure that this is shown for the plane. I think that in the same place it's shown for this context, but I'm not sure. If I make any mistakes, it's my fault, not fault of the conc. I think he can explain. Okay, so all mistakes are mine. All results at least so far. So let's for a moment believe in that. And the good thing here is that this function, it's algebraic. I'm sorry. Algebraic.
Break it in half.
Yeah, usually.
Oh, that's better thing. Of degree at most 2 to the m. So this comes from so-called transformatics method, but this can be shown without much pain. So this is an algebraic function, and you can compute it very efficiently, because if m is relatively small, then you have some matrix, and you compute it. Matrix you compute its eigenvalue, so you can get this for m, and then this would mean that you can compute with this gm of p with good precision. So, and then the next step would be say the following. So let me put it here. So then we can compute this theta m, and then we can compute yeah, of course, both of these errors require some work, but on a high level we can do that.
But m cannot be too big, so...
Yes, of course, if m is large, then we cannot. I mean, there is certain certain restriction in sense of complexity. Sure. So, and what we can now say, it's called statement, is that Gm of P is less than or equal F2 of P. And this statement I don't want to believe, because I think this is one I can just prove now, because I want to prove something. So, why is it true? Okay, let's see. So F2P, I can write it as limit of subsequence. P and N square. But that's what I can say. So this is number of tilings. This is number of tilings of n times n squared times. And then what I can do, I can divide it in strips of size m. For each strip, I have number of tilings A, B, M, and N. So if I have density P in each strip, then I have overall density P also. So this number is at least nth power of this number. Okay? Because I can just divide and tile separately. So this is at least n times and then P now for strip. And then you can just cross one of n's. And this will be the definition of GM. Again subsequence, but I need all analytical subtleties. Okay, is it fine? So, and this means that this energies of strips, they bound my plane energy from below. And if I compute like energies for wide enough strips, that what can I do? I can hope that maybe they will be close to the plane energy. This is fine. And this is actually gives some idea. But then a very nice thing comes. So what Hong says, let's consider a little bit different strips. Okay, so let's introduce A, B, C, and N, where C here is not a degree, maybe it's a bad notation, but let's think of this one. This will be the number of tilings with all the same properties, so that the number of dimers is, where is it? Is this one. But now we tile not rectangle, but a cylinder. So, and here, and what I can do, I can put dimer here, and it will like return here. You know, like in computer games, so you go up, you go up and down. So, like, this is the same as this.
How about left and right? Is that the same?
No, I will take cylinder.
It's not symmetric.
It's not symmetric, and the reason is that it's not important. I mean, I could glue this also, but it will give the same result because somehow this will go to infinity, and that's it. It will play a role in final limits. But if you have just finite interval, if it's glued or if it's not glued, it will disappear after logarithm and dividing. So I could glue them, it will yield the same result.
But it's easier not to make it a doubles?
It's just easier not to make it doubles. Just so, and then again I can also consider the limit. This will be G C of n. This will be P. Okay, so the same definition as I had for G there.